So let's see the verification of superposition theorem. So we are aware that the superposition theorem can be applied when the circuit is more complex, where we cannot apply mesh and nodal analysis explicitly because we have many number of meshes and many number of nodes. So in those cases, superposition theorem will be very handy to solve. So this is a circuit diagram where they ask us to find Vx by superposition theorem. So we have to find out the value of Vx with the polarity at the top it is positive and at the bottom it is negative. So let's go on to see with theoretical calculations. As you are aware, the number of steps involved will depend upon number of independent sources. So we have 1 amp, 3 amp, 2 amp and 30 volt. So we have 4 independent and 1 dependent. So the number of steps are 4. One with respect to 1 amp, we call that as Vx dash. Second step, for example, with respect to 3 amperes, we call Vx double dash. Third step with respect to 2 ampere, we call that as Vx triple dash. And the last step with respect to 30 volt, we'll call that as Vx4 or Vx4 dash. Right? And then what we do, we add all the voltages according to that given polarity, that is top positive and bottom negative, we get the total voltage Vx. So in this way you can see how we can break down the complex circuit into simple circuit. So in the given circuit we have 1, 2, 3, 4 meshes, and you can see here we have only 2 meshes, and the last step Vx4 we have only 1 mesh. So in this way we can reduce the complexity of your given problem. Now I hope you know here how we have reduced. So let me just re-emphasize on that. So when you are solving with respect to any one source, rest all voltage source you should short circuit, and current source we have to open circuit. In that way we have rewritten for Vx dash, Vx double dash, Vx triple dash and Vx4. Let's solve with Vx dash. Here I'll be solving with respect to nodal analysis. So I'll rename this Vx as Vx dash, similarly 6Vx as 6Vx dash. So I'll solve by nodal. There are only 2 junctions. So writing the equations for nodal analysis and then simplifying it for Vx dash, we get the answer for Vx dash as 1.33 volt. Similarly, I'll write down here this Vx dash is equal to 1.33 volt. Now we have to solve for Vx double dash. So Vx double dash, again I rewrite Vx as Vx double dash, and similarly 6Vx as 6Vx double dash. Again I'll apply nodal analysis. We have 2 junctions. Now this is the equations for your node voltage analysis, and then as I solve I'll get Vx double dash as minus 4. Next I'll write down that Vx double dash is minus 4. Next I'll solve with respect to 2 amperes, that is Vx triple dash. So here I'll rename Vx and 6Vx as Vx triple dash and Vx triple dash, 6Vx triple dash. I'll apply by nodal. So these are my 2 junctions. So by nodal I can say that node voltage V1 is equal to 6Vx triple dash. And what exactly? We have only 1 junction and 2 unknowns. So I have to equate what is Vx triple dash. So what is Vx triple dash? So Vx triple dash is nothing but I into 4. That is current in this orientation. And what is the equation of this current? It is given as V1 by 9. So I substitute that Vx triple dash is equal to V1 by 9 in the above equation, and when I solve, I'll get the answer for V1 as 0 volt. It sense that 2 amperes is not generating any voltage drop for or contributing the voltage drop across 4 volt, right? Now if I apply mesh analysis for the same sum, right, I consider I1 and I2 in anti-clock and I1 is clockwise direction. So we have only one unknown, I1, and I2 is clockwise in anti-clockwise, which is 2 amperes. And the equation for Vx triple dash is minus I1 into 4. Now when I apply for mesh 1, this is my equation, and again Vx triple dash is nothing but minus I1 into 4. So when I substitute that, I get that as minus 24 I1 plus 9 I1. And when I solve, I'll get the value of I1 0, and in turn my Vx triple dash 0. So you have seen that I have just verified that Vx triple dash is 0 either by nodal or mesh. So you can do it only by any one method. So I just did this just to show you that it is still 0 volt. That means 2 amp is not contributing for any voltage drop across 4 ohms. So we write Vx triple dash is equal to 0 volt. Last, with respect to 30 volt, it's a simple single loop. So let's first replace Vx in 6Vx by Vx4. So let's assume the current in clockwise direction. This is my mesh equation. So as we solve this, we have 2 unknowns here, but we have only one unknown, that is I. So what is Vx4? Vx4 is nothing but minus I into 4. I hope you are aware that why we have minus 4. So according to this KVL current, we will be marking here positive and negative. This is our KVL. So that is why you can see here we have plus 4I. But what is this Vx? Top I have positive, right, and bottom I have negative. And this current hits negative. That's why I have written here as minus I into 4. So as I solve, I get the value of I as 2 amperes and similarly Vx4 as minus 8 volt. So these are your answers for Vx dash, Vx double dash, triple dash and Vx4. And what you have to do now? Sum of all this will give you Vx. So Vx is nothing but sum of all these voltages will give you the answer, that is minus 10.667 volt. Now, when you apply mesh analysis for this circuit, okay, so let us say this is your main circuit, circuit 1 is your main circuit. If you apply any method, right, source transformation, source shifting, mesh or nodal, any theorem, I mean any other way of solving this, you will still get same answer for Vx, that is minus 10.667 volts. Right? So now let us move on to simulation and check your answers. So these are the calculated values. Right? So with respect to Vx dash 1.33, Vx double dash 0, with respect to 2 amperes we got minus 4, with respect to 30 volt minus 8. The total answer is minus 10.667 volt. Right? Circuit connection in PSpice. So these are the components. We require one VDC, we require 3 current source, 1 amp, 3 amp and 2 amp. We require 2 passive elements, 4 ohm and 5 ohm. We require 1 ground point and we require 1 dependent source, and that dependent source is known as E. So this E is a part name for the dependent source, and this is actually a voltage dependent voltage source. So now we'll move on for simulation. So what all parts are required? First let us take resistance and place them in order. I have 4 and I have 5. Let us take VDC, and we need current source, that is the part name is IDC, and let us place accordingly. Let us this is going downwards, so we have 1 amp going down. Let us rotate. We control R, 3 amp and 2 amperes, and we need a part name called E, that's your current voltage dependent voltage source somewhere here, and we require a common ground, that is E, G and D. Right, let us zoom in and let us connect them. And this 3 amp current source is connected before this 5 amperes. Now we can see we have a dependent source here. The one which is inside the circle is plus minus. Right? So similarly here within the circle there is your plus minus. Plus is connected at the top and negative is connected after 5 ohms. Right? And your dependent parameter is Vx. This is a dependent parameter. And where is the dependent parameter? It is here. Top positive and at the bottom it is negative. Right? So at the top you can see this is positive. So this has to be connected here. And at the bottom it is negative. So this has to be connected here. Right? And this is actually your 4 ohm resistance. Right? And this is your 30 volt. This is 3 ampere. This is 2. This is 5. Let us connect your ground terminal. And this is 1 ampere. Right, I hope we have revalued everything, but we have missed. What we have missed? We have given the dependent parameter, we have given Vx, right? The value 6 we have missed. So double click, you can see default value gain is 1. So revalue this to 6, save attribute and click on OK. And now we have built the circuit. Right? So let us save the file. Transients, just enable transients, and we want to see voltage, go to marker, mark voltage differential, positive and negative. Now I want to see Vx, double click on R1 and rename this as Vx. Now simulate and check your answers. Click on toggle cursor. Yes. You can see at any point of time my answer is minus 10.667 volt. Now what we have got Vx. You can see it is Vx. But what do we want? Now this is important. We want to verify for Vx1, Vx2, Vx dash, Vx double dash, Vx triple dash and Vx4. Now how do we do that? Now please kindly analyze here. I'll try to trim my circuit so that you'll understand as I do it. The trimming part you have to be careful. It might change your circuit. So as you build, right, you can see I have a connection here. I should not have got that. Now if I simulate, you can see that I'll get a different value. So you can see I'm getting as minus 6 because the circuit has changed. Now if you see the circuit diagram, this is not connected. It is not. Let us see where this has connected actually. So you can see negative is connected after 5. Right? It has to be connected after 5. So this I have to trim. So when you trim the circuit, you have to be careful in that. So or else what you can do, as you build the circuit, make sure it is not very big. The reason why you have to trim, I'll tell you. Now, so I have reduced the circuit. You can select everything and you can shift the circuit above. Right? Now let me just simulate again after trimming, just to make sure that I have the same voltage for Vx. Yes, I have minus 10.667 volts. So it is still same. Now what I do is I will delete this positive and minus. This is very important. Now I'll use this ABC just to draw text, and I'll call this as main circuit, or I'll say here as Vx. Okay. Now I'll save the file. What I'll do is I'll copy the entire thing. Control C is a shortcut to copy and Control V is paste. Now we have until Vx4. So I'll paste this 4 times. 1, 2, 3 and 4. Now this is my circuit, right? To find, for example, the first one was, let us go back again and see our calculus here. So Vx dash was with respect to 1, Vx2 was 3 and then 2. So let us name the circuit in that syntax. So here I'll say to find with respect to 1 ampere, and let us enlarge this. So to find with respect to 1 ampere, and let us say the next one is with respect to 3 amperes. So let me type in that way, to find Vx with respect to 2 amperes. And similarly this one is with respect to find Vx with respect to 3 amperes, and this is with respect to 30 volts. Right? So how do we eliminate? I'm solving with respect to 1 ampere. Just revalue this 30 to 0, current to 0, this current also to 0. And I'm solving with respect to 2 amperes. Apart from 2 amperes, rest all active elements has to be replaced with 0. And I'm solving with 3 amperes, 1 amp is 0, 30 volt is 0, 2 amp is 0. With respect to 30 volt, 1 amp is 0, 3 amp is 0, 2 amp is 0. Right? So now I will save the file. Now to find Vx, I'll again go to marker and place my potential difference. So I'll place here plus minus, I'll place here plus minus, I'll place here plus minus. Now do not place your marker and then copy, you will get error. Kindly do the way I am doing. So I'll call this as Vx1, right, or Vx dash. I doubt when I simulate I get an error. Let us check. And I'll call this as Vx double dash. and this is Vx triple dash, and this Vx as Vx4. It says no space, so what I'll do is I'll put a dash. Okay. Right? So when I simulate, let's see what output do we get. So it says name r underscore Vx is defined more than 1. So let's go and debug the error. We will rename Vx as Vx1, this is Vx2, this is Vx3, and this is Vx4. Let us try to save and simulate now. Yes. Right? So where is Vx? This is my Vx. So the answer is minus 10.667. Vx1. So let us now verify our answers. So we have done circuit simulation. Let us verify for our simulated answers. Right? Yes. Now Vx we have got as minus 10.667. So this is your Vx minus 10.667. Vx dash or Vx1. This is Vx1. We have got 1.33. Yes, we have got 1.33. Vx double dash, that is equal to 3 amperes. That is nothing but Vx2. We have got 0. Yes, we have got 0. Vx3 or Vx triple dash is minus 4. So let us see here. Yes, we have got minus 4. Vx4 or Vx4 dash is minus 8. Let's click here and check. Yes, we have got minus 8. Thus, we have verified your superposition theorem. So without applying superposition theorem, you are getting the answer as minus 10.667, and after applying, how do you verify that? I am verifying for Vx dash, Vx double dash, triple dash, Vx4 dash. We've got the answer, right? And we also verified for your main circuit that it is still, without applying superposition theorem, it is minus 10.667, right, volts. So this is how one has to simulate for your superposition theorem.